Now let's have a second look at our block diagram system that we just started with and see if we can simplify it a bit more in order to be able to use it easily, let's say, throughout the course. So over here you can see again the initial block diagram system that we have for our closed loop linear control system with the transfer functions for input transducer, output transducer, and the rest. And now we are going to make it, let's say, more compact and more simplified. If we consider the transducers, they are usually in the form that they have a very fast dynamics. And since this is a property that they have, that we can usually replace them by their DC gains and then approximate them as some static systems. So if we do so with, instead of GT0 of S, so GT0 of S will be replaced with GT0, and then GT of S will be replaced by GT itself. Okay, so these will be some constant values, let's say, the DC gain of the transducers. Then on the other hand, we are interested in finding a unit feedback loop. However, if you have a second look at the initial, let's say, the block diagram system that we had the GT over here, yeah. So initially GT was in the feedback path. If you want to have some unit feedback loop, we need to move it and bring it here. That's why you see GT appearing here, which is multiplied by GC of S, which is a controller. So it has moved after the first summing point and then after the second one, and in order to have it follow in the rules that we have for moving the blocks after the summing point, we see that it appears here in the form of GT inverse and GT inverse over here. So basically, if you compare the signals that we have in this system with the original one, they should be the same or in every place in it. Okay. So once we do this, let me just remove GT from here. The new, let's say, form of our closed loop block diagram system will be similar to this, and afterwards we can indeed assume that we are receiving the disturbance signal in the form of D, the noise signal in the form of N, and the reference signal in the form of R. And once this is the case, we can neglect HP. So we don't, let's say, care about that. We neglect GT inverse times HT and GT0 times GT inverse. So we just neglect these and assume that we have received R as the reference input, N as the noise, and D as the disturbance. We just do one more step over here. By indeed swapping the position of these two summing points. Okay, so if we do so, the noise signal will be considered to be applied after the reference point, but it will not change the behavior of the system. It will be indeed the same system, because we can obviously swap the position of the summing points. One more thing to consider here is that we have gt times gc bar of s as the controller. We also replace it with gc of s, which is the transfer function for the controller. However, we should also keep in mind that this gc of s is equal to gt, which is the DC gain of the transducer, times the gc bar of s, which will be the actual controller. So gc bar will be the actual controller, but in our designs we will find out in the gc of s. If you want to implement it, you should keep in mind that it should be divided by gt. If we do so, we will end up with the block diagram system, which is shown here. We are going to use this as the standard control loop throughout the course. Over here we have the reference signal as the, let's say, main input. Then we have the noise as another input and disturbance as the third input. And C will give us the actual output of the system. The controller is in the form of GC of S, and the actuator plus process is given as GP of S. U is the control input to the system, to the actuator and process, and E is the error signal. And you can see that E is obtained as R minus C. So R minus C gives us the error signal. And as we will see later, when we want to design the controller, our aim will be to make error as small as possible. So we'll try to make it 0, but we will do it in a quick way as well. Alright, so we will use this, let's say, as the standard control loop again. However, we should also keep in mind that there are the blocks that we just have seen: HP of S, HT of S, GT0, and GT. Over here you can see the details regarding the standard control loop for the DC motor. For the DC motor, we already have obtained the block diagram system. Now we assume that we have numerical values for the parameters of the motor. J, B, K, R, and L are given, and therefore the transfer function that we obtained for GP of S will be equal to 0.01 over the denominator, as you can see here. We can also replace the values for the numerical values for the parameters for the HP transfer function that we have for the motor, and it will be given as 0.5 s plus 1 over the same denominator. The input and output transducer transfer functions could be approximated with their DC gain. For GT0 we will have 0.06 volt per degrees, and for GT of S we will have 0.02 volt per radian per second. And if we consider the reference R in radian per seconds, the reference signal, we can convert the angle of the knob of the potentiometer, which is R0, to R as GT0 GT inverse R0, which will be 3 times R0. And you can see an example here. If R0 is equal to 20 degrees, the corresponding reference velocity will be equal to 60 radian per second. And the voltage that the corresponding voltage that we get in the form of R bar will be 1.2 volts. Let's say someone has designed a PID controller for the system in order to control the speed and make the error getting as small as possible. GC of S, the controller, is given in the form of a transfer function s squared plus 100 s plus 200 over the given denominator. And then if we implement it as an analog signal, now this is something that you should keep in mind. we should consider the effect of GT. So GC bar will be the controller that we are going to implement, and GC is the controller which is obtained, let's say once someone wanted to design the controller in order to control the behavior of the DC motor. Okay, now few more points. In general, for our standard, let's say, closed loop system that is shown here, we have some expectations. These are the ideal things that we want to happen. We want to have perfect tracking, which means that we want to have always C being equal to R. C should follow the R perfectly at all times. And we want the system to be insensitive to process disturbances. So C will follow R for all time, even if there is some disturbance. It should be insensitive to disturbance. It should be also insensitive to measurement noise or N. C should be following R for all realizations of N. And the value of another fact is that the value of U, the output from the controller, which is being applied as the input to the process, should always remain small. And this is the fact that we want to have in order to not to damage the system. But these are something that we want to have ideally. But in practice, these are not achievable. On the other hand, in practice, these are what we are going to obtain. The first fact is that we want to have the closed loop stability. The closed loop system must be bibostable, which means that for any bounded realization of R, D, and N input signals, it should give us C, U, and E signals remaining bounded. Keep in mind that C is the main output, U is the control signal, and E is the error signal. The next thing that we are going to obtain in practice is tracking, which means that given a reference R, the reference signal, we want to have the smallest possible error between the reference and the output, both in the transient and in the steady state. Later we will see the difference between transient and steady state behavior of the system. However, tracking means that the error should remain as small as possible. The next point is regarding the robustness. We want to have our output following the reference signal closely enough, even when there is the noise and disturbance, let's say, available. So the existence of the noise and disturbance should not affect the output signal greatly. We try to minimize their effect. The next point is regarding the sensitivity. The controller should be designed based on a nominal plant model. So we will have the model of the plant, we will design the controller for that, but the actual plant might be a bit different than the nominal plant model that we have. However, we want our system to be insensitive to the changes that we might have in our plant. Later we'll discuss this in more details, but for now we can consider that some parameters of the model that we have for our plant might be different in the model and in the actual plant. And we want to have our system as insensitive as possible to that. And the next fact is regarding moderation of the control action. The control variable U shouldn't exceed given bounds, otherwise it will damage our system. So these are the things that we are looking for in practice, and we will see how to deal with them in designing the controllers later.